Alright, so today we're going to start Unit 5, and that's your proof unit. And we're going to start with identities. So 5.1 is identities, and these 5 statements right here are identities that you should be familiar with. So the first identity is cotangent of x is equal to 1 over tangent of x. Because tangent's reciprocal is cotangent, or you can say that the other way around. Cotangent of x's reciprocal is 1 over tangent x. Okay? Cosecant of x is the reciprocal of sine x. So cosecant of x is equal to 1 over sine x. Secant of x is 1 over cosine x. These bottom two identities are things we talked a lot about while we were graphing. So we said that tangent of x is equal to sine x over cosine x, and cotangent of x is equal to cosine x over sine x. So hopefully these things are things that you are familiar with, and if not, I would recommend putting these to memory. Alright, so let's start off with this statement right here. What is tangent of x times cotangent of x? So if you know the answer to this immediately, then that is great. You have a very good understanding of reciprocals already. But let's just go ahead and show what it is. So tangent of x, you could say is sine x over cosine x. And cotangent of x is cosine x over sine x. And we know that when something is on bottom that you see exactly on top, that they end up canceling each other out. And that when something, once again, that is on top that's also on bottom, they will also cancel each other out. Now when you cancel fractions, the top still exists at 1 and the bottom still exists at 1. Not at 1 necessarily, but I mean you have times 1 here, times 1. So you get 1 over 1, which is 1. So the answer to this is 1. Now, if you were thinking, Miss Stapleton, why did you do sine x over cosine x and cosine x over sine x? Why didn't you just do tangent over 1 times 1 over tangent? Well, that's perfectly fine too. You still would have gotten tangent on top, tangent on bottom. They still would have canceled. You still would have got 1. The reason why I did this way is because honestly, remembering tangent is sine over cosine is usually more helpful. Cotangent is cosine over sine than doing it this way. I'm not saying that this isn't going to work, but this is, it's just more complete way to show it. And that's one of the reasons, though, that this is a really hard unit for me to teach, is because there are so many ways to do these problems. So just because I may do something in class doesn't mean it's the only way to do it. So if you ever think you've found another way, if it works, it works. And so you can call me over and I'll come over, or you can come in the morning and we'll try to see if that works. Alright, so for those same reasons, these are also going to be 1. Sine x, since that's just sine x, there's not really anything you can write instead of sine, so I'll just put that over 1. And then cosecant, we want to say is 1 over sine. I just have to delete that whole thing now. Perfect. Alright, so I'm here. So sine x over 1 and 1 times 1 over sine x. So the sine for sine cancels, and we end up with 1. Okay, and for that same reason, you can see that that's going to be 1. Because the shorthand way to think of this is just the reciprocals multiply to 1. Alright? Alright, let's go on. Alright, so let's start with example 1a. Tangent of x equals secant of x over cosecant of x. Now, when we have fractions such as this, usually if you can, you would want to work with them to do something with them. That doesn't really make sense, but secant of x over cosecant of x. The problem is that secant of x and cosecant of x sometimes are less familiar to us than sine and cosine. So the first thing you might want to do is change them to sine and to cosine. So secant, whose reciprocal is cosine, so that means that we're going to have 1 over cosine x, and cosecant, who is the reciprocal of sine, so 1 over sine x. So all I've done is, instead of writing secant, I've wrote 1 over cosine, and instead of writing cosecant, I've wrote 1 over sine. Well, we've dealt with this a few times before, where you have this big fraction, or a fraction over a fraction. Let me just come over to the side and do some quick recall, I guess. So when you have, okay, let's go back and say if we did 2 pi over 6, a lot of you are so used to this and you just know it's 12 by now, but how did we do that? We said, well, to put 2 pi over 1, 6 over pi is going to be what we multiply by to get rid of that bottom, and then what you do on bottom you must do on top, and so that's how we got to the 12, and all of this is gone. So do that same idea, but for my trigs. So if I'm going to multiply times this guy to get rid of home, I'm going to multiply times sine x, and I'll go ahead and still say over 1, just to kind of very slowly show multiplying this. What we do on bottom, we have to do on top. Remember, this is what I call the magic number of 1. And so what ends up happening is, of course, on the bottom, it all goes away. So sine x cancels with sine x, and 1 still cancels with 1, even though that's kind of silly, but still nonetheless. And this is all multiplied, just like the bottom was. So when we multiply, 1 times sine x is just sine x, and cosine x times 1 is cosine x. Okay, so that's it. Because sine x over cosine x, go back to your identities. So at the very top, if you go back to the identity, sine x over cosine x is, in fact, tangent of x. And that is your very first proof. All right, let's go on. So make sure you have this written down. I'm about to delete it all. All right, so if we apply the same idea to b, now, again, a lot of you may think of this as a different way. The shorthand way to what we said earlier is that if you see a cosecant on top, so we see a cosecant on top, that could be written as a sine on bottom. So instead of writing cosecant on top, I could write sine x on bottom. And if I see a secant x on bottom, I could rewrite that as cosine x on top. Now, this is what we just did. It's just a much faster way to do it. So if you understand this, that is so great, because now you're done. Cosine x over sine x is cotangent x. So again, this is just another way to do it. If you want to go back and do it the other way that we just did, so let's just pretend like this is a new problem and I haven't done what I just did. So I know that cosecant of x is 1 over sine x, and I know secant of x is 1 over cosine x. And then I could multiply times cosine x over 1, cosine x over 1. This goes away, and this multiplies to that, and you still get cotangent x. So this is me just attempting to show you that there are so many ways to do these. And I'm going to try to show you as many as I can, but I'm not going to be able to show you all of them. So if you really believe that your way works, like I said, just come and ask me, and I'll tell you if that's a good way. If it works, it works. But I just got to make sure you don't make a mistake or something. All right. Pythagorean theorem identity. So we know, based on Pythagorean theorem, that legs squared equals hypotenuse squared. So x squared plus y squared equals r squared. That's what this basic Pythagorean theorem is. Now, if we want 1 to be on this side, so if we look at this, in order to get 1 on this side, then I would do divide by r squared, divide by r squared, and you get here. Well, let's take a look at x squared over r squared. X squared over r squared, that's adjacent over hypotenuse when we talk about trig, because this is where my theta is. And adjacent over hypotenuse is cosine. So that's why x squared over r squared is cosine, y squared over r squared is sine squared, and we get equal to 1. So this is our first identity. So what an identity is, Pythagorean theorem is an identity. It's something accepted as true. We manipulated the Pythagorean theorem, and we got the identity cosine squared plus sine squared equals 1. For some reason, when they say it, people usually write sine squared plus cosine squared. It comes off of the tongue easier. There's not really a difference between these two. It's just, this is, I don't really care what you do. Okay, now if we take that sine squared plus cosine squared equals 1, so if I take this identity, I can make actually a total of 8 more. So how I can make 8 more is if we just write this down, sine squared plus cosine squared equals 1. Well, let's say for some reason you want to see tangent. If you want to see tangent, tangent is sine over cosine. So I see my sine here, and if I divide by cosine, I would create a tangent. So as long as you do something on every single piece, over tangent squared, not tangent, I'm sorry, over cosine squared, and we have to do it on every single piece. That's what makes it fair. So as long as I divide every single piece by cosine squared, then I can come up with a new identity. And that new identity is based on what is sine squared over cosine squared. Well, sine over cosine is tangent, therefore sine squared over cosine squared is tangent squared. Cosine squared over itself, anything over itself, is 1. And then 1 over cosine squared is secant squared. So this is a second Pythagorean identity. So that's what this guy says. If you use that same logic, go back to the original. Now if we divide by sine squared everywhere, we can get this one. All right, so let's go on to some examples. So transform sine x times cotangent x to cosine x. So if we start here. So you may want to rewrite the problem again. And since I'm trying to end with just a cosine x, then I really probably only want to see sines and other cosines. So what my first step is going to be is to say, well, sine x, that's a pretty friendly trig. We know a lot about sine. But cotangent x, I'm not that familiar with. I would rather see cotangent in terms of sine and cosine. So my very first step, so how you should do these is you should write equals to show that you're going on to your first identity. And so when you write equals, you're going to write, well, which one are we going to be changing? I really only want to change cotangent of x. So when I rewrite sine x, I'm going to rewrite it as sine x, but I'll go ahead and put it over 1 because I'm about to start seeing fractions. And then when I rewrite cotangent of x, so I'm going to rewrite this in blue, cotangent of x is cosine x over sine x. Well, at this point, you can see that you're basically done, because what we have is we have a sine on top and we have a sine on bottom. Anything on top that's also on bottom, when it's getting multiplied, cancels, and we end up with just cosine x, which is where we wanted to end. All right, this next proof, cosine squared minus sine squared to 1 minus 2 sine squared. What you have to remember for this one is go back to the Pythagorean theorem that we just did. So I'm just going to write those down because it's hard for me to flip back and forth. But the reason why I know to do this is because anytime you see a trig squared or even a 1, you're probably going to be using some form of that Pythagorean theorem. So you don't know which one it's going to be necessarily, but you're going to be using some form of it. So cosine squared plus sine squared equals 1. Well, this is interesting because if I am starting here, let me just rewrite that. I do recommend that you rewrite it. And this is where I'm ending. Well, I can't, a lot of this is about like replacing. And we don't have exactly cosine squared plus sine squared. We have cosine squared minus sine squared, but that is not exactly cosine squared plus sine squared. But what I can do is I can take my Pythagorean identity and I can manipulate it even more. So what I mean by that is, let's think about the fact that this is basically like an equation. It's an equation just like a plus b equals 1. Well, let's say for whatever reason you wanted to get a by itself. Then you could say that a equals, and if you take away b from each side, you have 1 minus b. So a equals 1 minus b. Or anything like that. Alright, so the problem is that since I see a cosine squared here, and I don't really see one here, I gotta think of how else I can write this. So I was talking about this, and since I have cosine squared plus sine squared equals 1, what I'm trying to do is change cosine squared. So if I'm trying to change cosine squared, I want to, so to say, isolate cosine squared. So if you take away a sine squared from both sides, you can get cosine squared equals 1 minus sine squared. So this over here is just kind of like some side work I'm doing so that I can figure out what I can do to change this. And what I'm going to change it to is 1 minus sine squared, because that's what cosine squared is equal to. So 1 minus sine squared. Now, I still have this minus sine squared. I didn't touch him. Now, let's look at what we got. We got minus sine squared, minus sine squared. Well, that's 2 sine squareds that are being minused. So 1 minus 2 sine squared. And that's where we were trying to go. Alright, next, cosine m minus secant m squared. So if I rewrite that, a lot of this is algebra. So the reason why I say that this is algebra is that you have to remember when you get something squared, what that means is that you take the parentheses and you multiply it times itself. And now what we have to do is we have to FOIL. this times this. Well, that makes cosine squared m. Now, cosine m times negative secant m is minus cosine m secant m. Now, negative secant m times cosine m and lastly, negative secant m times negative secant n does make positive secant squared m. Now, I did this in a long version because I had assumed that this would be how y'all would do this, but these guys right here are called reciprocals. We talked about this on the front page. And when they multiply to 1. So I have cosine squared m minus 1 minus 1 plus secant squared. And now if you go to your formula chart again, this, you can see, is actually a negative sine squared. There's no reason why they're using m instead of x. I almost just wrote x there. And this would be, you could write plus right here, so plus tangent squared. Because you know minusing 1 is like plus a negative 1. And this I can replace with tangent of squared. Alright, and that's it for today's notes.